2.7, apply the fundamental theorem of algebra. Repeated solution. We have a degree 3, and when all is said and done, we have the factors. X would be x equals -3, 4, and 4. We're going to be seeing how these even multiplicities are going to be affected on the graph. The fundamental theorem of algebra, if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. We also see by the corollary, if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solutions. Each solution repeated 3 times is counted as 3 solutions, and so on. Example 1, how many solutions does the equation have? On A, how many solutions do you expect? What is the degree of the problem? The degree is 3, so we expect 3 solutions. Go ahead and try example B. Example B is a degree 4. We expect 4 solutions. Now, when you see that I've given you a half a sheet of paper and there's only one example on it, I like to just cut off the example so that I have all of this room to be able to do my work. This is a degree 5, so it's going to be a little bit of work to get the 5 solutions. We would start with first our possible rational zeros. So we have P over Q. Our possible rational zeros is going to be factors of 14 over factors of 1. So basically, it's going to be plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14, all over 1. The next thing we're going to do is synthetic division. We have degree 5, 4, 3, 2, 1 in the constant, so we're all set on our descending order. Filling off the coefficients, we get 1, -4, 4, 10, -13, -14. Doing our synthetic division, trying to find some solutions here. We have okay, there's our first solution, -1. All right, we're looking for another solution here. And 2 is also going to be a solution. Bringing down our 1 times 2, -5, and 2 is -3. -3 times 2 is -6. 9 minus 6 is 3. 3 times 2 is 6. 1 plus 6 is 7. 7 times 2 is 14. And -14 and +14 equals 0. We have a degree 5 down to a degree 4 down to a degree 3. So we need to divide one more time. And then we can factor or use the quadratic formula. All right, there's no way I'm going to get a 7. I've tried all the factors, and I tried all of the factors to show you that I didn't get any more answers. Well, -1 or 2, maybe one of those is a repeated factor. Let's try -1 again. And this is looking promising. All right, so -1 works again in our polynomial, that a degree 3 here. Bringing down the 1, 1 times -1, -3, -1, -4 times -1 is 4, and 4 and 3 is 7. 7 times -1 is -7, and we get 0. We have a degree 3 that is now a degree 2, and we are ready to factor or use the quadratic formula. Bringing down all of my factors, we have x plus 1, and we have 2 of those. We have an x minus 2, and then we have our quadratic, x squared minus 4x plus 7. We're going to set them equal to 0 and solve. So factors of 7, factors of 7 will not add to 4. Quadratic formula. Negative b is going to be a positive 4 plus or minus b squared, -4 squared minus 4 times a times c all over 2 times a. We have 16 minus 28. So we do have an imaginary solution here in the complex plane. And we are going to simplify. We get x equals 4 plus or minus I for the negative, and then the square root of 12. That is the square root of 4 times the square root of 3. So that's going to be 2 square roots of 3. And now we see all 3 terms have a 2 in common. We're going to divide by 2 on all 3 of these terms. Finally, we get x equals 2 plus or minus, so dividing by 2, we have I square roots of 3 over 1. Okay, our final answer then, what says find all the zeros. It's important to make sure that you read the directions. Are we looking for zeros? Are we looking for factors? Students lose a lot of points on quizzing and testing because they're not giving exactly what the question's asking for. Sometimes it's going to be factors. Here we're looking for the zeros. We have x equals -1 multiplicity 2. We have 2, and we also have 2 plus or minus I square roots of 3. So we've got 2 answers here for the -1. Here's our third answer, and then here are 2 more answers here, 2 plus I square roots of 3 and 2 minus I square roots of 3. These are all the zeros. It said all zeros, not just real zeros, all the zeros. Final answer. Behavior near zeros. When we have a factor, x minus k, and it's raised to an odd power, it crosses the axis at that k number. So here we see that at 2, it's crossing through the x-axis. That means there would be an odd number of solutions for this. It could be just 1, 2, it could be 3 2s, but it's odd. It's being raised to an odd power, therefore it's crossing the x-axis. When we have a factor and it's being raised to an even power, then it is tangent to the x-axis at x equals k. What does it mean to be tangent? Tangent means that the function is going to touch at a point. We can see here on the graph that at -1, the function is tangent at that point. It's just touching it at one point and then it bounces off. Another way that we like to think about the even power is that it bounces off the x-axis. It's approaching -1 and then it bounces off and turns and goes back down. That is for an even degree. So an odd degree crosses through the x-axis. The even degree is going to bounce off the x-axis. When we're analyzing polynomials, we've been talking about the end behavior. The end behavior is where the tails are. Where are they going? Now we're looking at the behavior as it's approaching the x-axis. Is it an even power and bounces off, or is it an odd power and going through the x-axis? From quadratics, we had the conjugate root theorem. If we have a plus the square root of b, we know that we also have a minus the square root of b. And that would also be true for a plus bi. We also have a minus bi. And these can be seen from the quadratic formula. Write a polynomial function f of least degree that has rational coefficients and a leading coefficient of 1. All right, this is not typed correctly. So it has a leading coefficient of 1, and three and 2 plus the square root of 5 as zeros. So we have a leading coefficient of 1, and we have 3 and 2 plus the square root of 5 as zeros. What do we know about our zeros? We have x equals 3. We have x equals 2 plus the square root of 5. If we have 2 plus the square root of 5, then by the conjugate theorem, we know that we also have x equals 2 minus the square root of 5. These are all the zeros that we have. We already know what degree our function is going to be then. This is going to be a degree 3 by the time that we're done. We have a leading coefficient of 1, so we know that it's a positive degree 3. We are starting at the end of the process. We are working in the reverse process. We have been starting with the polynomial, and we were able to come down and factor the polynomial and then solve the polynomial. This is where we're starting right now on the example that we're doing. We're given the zeros and we need to work back to the polynomial. So what is the step That's before the zeros, putting them into their factors. I'm going to put the 3 back on the side with the x, so that would be subtracting 3 from both sides, and we get x minus 3 for a factor. We get x minus 2 and minus the square root of 5. On the next one, we have x minus 2 plus the square root of 5. You will always multiply your square roots or your imaginary numbers first before you try to combine them with other numbers. So we're going to start here by multiplying these together. What we want to do here is group together x minus 2. When I group x minus 2 together, I can just think of it as one single term. I have the first term plus or minus the second term. That would be the same idea as a plus b times a minus b. What do we know about factors that have exactly the same thing in both parentheses, but they have a plus or minus? What do we expect to happen? We expect that there will be no middle term. That is why we like to group these together in this way. We have our a term is x minus 2, and our b term is the square root of 5. And then we have a plus and minus. All right, so we have x minus 2 times x minus 2. That's going to be x minus 2 squared. And then we have, I'm going to show the entire example here for our notes, but ordinarily we would just skip that middle term. We have x minus 2 times the square root of 5. That would be the square root of 5 times x minus 2. Now moving on to my next term, I have negative square root of 5 times x plus 2. That's going to be a negative square root of 5 x plus 2. And then we have the negative square root of 5 times the positive square root of 5. Negative square root of 25. We still have x minus 3 out front. Here we see that we have the positive square root of 5 and the negative square root of 5 times x minus 2. Those are going to cancel, just as we expected, with the difference in sum. We are left with x minus 3 times, we need to expand out x minus 2 squared. We are going to practice using the binomial squared without having to expand it out. But if you need to go off to the side and do x minus 2 times x minus 2, then that's what you will do. Here we're going to practice expanding the binomial squared. The first term is x squared. The second term is going to be 2 times the first term times the second term. And then we have negative 2 squared, which is positive 4. And we also have minus the square root of 25, so minus 5. Simplify x minus 3 times x squared. 2 times negative 2 is negative 4, times x is negative 4x. And then we have a positive 4 and a negative 5. And now we're finally ready to multiply. Here we go. X times x squared, x cubed, x times negative 4x, negative 4x squared. X times negative 1 is negative x. And now we're going to move on to negative 3. Negative 3 times x squared is negative 3x squared. Going to put that in the x squared column. Negative 3 times negative 4x is a positive 12x. And then negative 3 times negative 1 is positive 3. Add it up. X cubed. Negative 4 and negative 3 is negative 7x squared. 12x minus 1x is a positive 11x, and then plus 3. Our final answer, x cubed minus 7x squared plus 11x plus 3. We started with the zeros. We have factors. We multiplied. And then we multiplied again. Example 4, approximate the zeros of a degree 6. We're going to use our graphing calculator because we're approximating. We have x to the 6th minus 2x to the 5th plus 3x to the 4th minus 10x cubed minus 6x squared minus 8x minus 8. Graph. This is a degree 6. I expect 6 answers. I'm going to fix my window in the standard zoom. It looks like the only zeros that we have are here, so I'm going to fix my x minimum and maximum. X min, let's go to -5 and 5. I'd like to see more what's happening down here in my y minimum. We can see the end behavior is a positive, even, facing in the same direction. We have these 2 zeros that we're going to approximate. Let's start with the one that's on the left. So we're going to go to calculate, second trace. We are trying to calculate a 0. Number 2. Left bound, if this is my 0 right here, when am I on the left-hand side of that? That would be on the top. On the top, I'm on the left-hand side of that 0. So I need to be on the top and hit enter. And then it's asking about right bound. Well, when am I on the right-hand side of that 0? When I'm down here, I'm on the right-hand side. Enter, enter again. And we get that the 0 is approximately -0.73. So x is approximately -0.73. And then we're going to calculate the 0 that's on the right-hand side. So second trace, number 2. Now, this is my 0. When am I on the left-hand side? That would be when I'm on the bottom. When I'm on the bottom, I'm on the left-hand side of that 0. Enter. And you can see that it's saying, okay, I'm going to start right here. Start looking for that 0. When am I on the right-hand side? When I'm on top, That would be when I'm on the right-hand side. Enter, and there's the other arrow that pops up, and the calculator is going to look between those two places, the left bound and right bound. Enter, and we get that that 0 is about 2.7. So it's also approximately 2.73.